Hello, everyone. My name is Vishali Patel. I'm the marketing director here at Quantic Electronics, and I welcome you to The Grid. The Grid is our monthly platform where we connect engineers with critical insights. If you have any questions, feel free to drop them in the chat below. We have folks in the background that are looking at these questions, and we're going to try to get to them, as many of them, before the end of the session. So let's get started. This month, we have Quantic Evans. Quantic Evans is located in East Providence, Rhode Island, and in Sanford, Maine. They create high power density hybrid capacitors for mission critical applications, from radar and laser to downhole drilling in electronic warfare. In today's webinar, Cracking the Code and Selecting Capacitors for Directed Energy Weapons, we have Misha Pierre-Mike, who's our sales and marketing manager, and also Nick Tukerko, who's our application engineer. And they will be diving into why capacitors are ideal fit. So over to you, Misha and Nick.
Thank you, Vishali.
You're welcome.
We can get that presentation started.
Right now. Here we go.
Great. Well, again, thank you, Vishali. My name is Misha, and I'm the sales and marketing manager here at Evans capacitor in East Providence, Rhode Island. Now, my degree is in electronics engineering, and I've been in the capacitor field in both engineering and sales roles for the last 12 years. As Vishali mentioned, I'm joined by our applications engineer, Nick Tukerko. Now, Nick and I have helped hundreds of engineers in the defense and aerospace industry choose capacitors for their unique applications, including for directed energy. We've learned about many of the common design challenges directed engineers face, including meeting aggressive electrical requirements, withstanding extreme temperatures, and meeting tight volumetric constraints. During today's webinar, we are glad to share some of the lessons learned and best practices we've gathered along the way. Next slide, please. Next slide. So think about the last futuristic sci-fi action movie or show you saw. Chances are that during some of the action scenes, the main characters were firing laser guns or laser cannons mounted on aircrafts instead of bullets and missiles. Well, we don't need to think about that as futuristic anymore because it's happening. We may not quite have a laser handgun yet, but there are most certainly directed energy weapons on aircrafts, ships, and land vehicles being actively tested and even deployed in the field right now with amazing results. Directed energy is widely considered the holy grail for missile defense, which continues to get a lot of attention as geopolitical landscapes change. Governments are pouring billions of dollars into ongoing research and development in this field. The DoD spends over $1 billion annually on directed energy research, so it's clear that the directed energy technology is the way of the future. Now, explosives and traditional kinetic weapons, such as missiles and bullets, will continue to have their place, but directed energy weapons will one day serve as a critical tool in the warfighter's toolbox. Now, despite the strong interest in directed energy weapons, several design challenges remain. Some key challenges include generating, storing, and releasing the power efficiently while mitigating thermal loss. While there is no silver bullet to these challenges, choosing the right energy storage capacitor can be a huge part of the solution. Next slide. So this webinar will consist of a high-level summary of what directed energy weapons are, how they work, and a review of the critical role capacitors play within them. We'll compare capacitors to batteries and highlight some differences between the two as power sources for directed energy weapons systems. We'll then discuss important capacitor design criteria to take into consideration when choosing one for a directed energy application. Then we'll compare some different capacitor technologies. Next slide, please. So what is directed energy? Now, the term directed energy covers a wide range of technologies, such as high power microwave, electromagnetic pulse, and laser. These weapons use electromagnetic energy to cause effects ranging from deterrence to destruction. Each type of directed energy weapon uses a different region of the electromagnetic spectrum. This spectrum describes all kinds of light, including those the human eye cannot see, and classifies them according to wavelength. Different types of electromagnetic energy have different properties. For example, the wavelength affects what the directed energy can penetrate, such as metal or human skin. Next slide, please. So there are other types of directed energy applications that are used in conjunction with kinetic and explosive weapons to improve their accuracy. We often think of lasers as weapons, but laser target designators use laser light to provide targeting for laser-guided bombs, missiles, or precision artillery munitions. LiDAR, another type of laser technology, is used by militaries for a broad range of defense applications, such as battlefield mapping, determining line of sight, and the autonomous navigation of military vehicles. Directed energy weapons have continued to gain increasing interest and support for a variety of reasons. Traditional weapons technologies have relied on the use of kinetic weapons and explosives to disable their targets. However, in some instances on the battlefield, kinetic weapons are not the most effective approach. Shooting down a $1,000 enemy drone with missiles that cost $500,000 or more is an extremely expensive defense method that has limited effectiveness. Now, kinetic weapons can also cause collateral damage, inadvertently damaging or even destroying friendly or civilian assets, thus creating the potential to cause political conflict. Directed energy weapons will one day become a key tool for warfighters as they offer a variety of advantages when compared to kinetic weapons. Electromagnetic pulse systems can disable swarms of hostile drones with precision while using artificial intelligence to distinguish between friendly or foe targets. Since they are only limited by available energy rather than physical munitions, directed energy weapons can have very deep magazines. In situations where warfighters typically send missiles that cost millions of dollars, directed energy weapons have a very low cost per shot. Next slide, please. So how does directed energy work in the first place? So although there are a wide variety of directed energy weapons, they really all do the same thing. They perform a task on a target with highly focused energy. Depending on the application, directed energy systems use varying amounts of energy. Some applications require a lot of energy in a small time frame, whereas others would require less energy for a longer duration. For example, laser designators and LiDAR systems consume less energy than high-power microwave systems, but they all rely on the same basic operating principles. So energy consumed per unit of time is defined as power. In other words, high-power applications, such as directed energy, use a lot of energy in a relatively short time frame. Using the equation on the slide, we see that as the time we have to deliver a specific amount of energy is decreased, the power output is increased. When thinking of different types of kilowatt and even megawatt lasers currently deployed, currently in development and test, we begin to understand just how much power directed energy systems put out. Directed energy lasers in the class of 100 kilowatts, even to 1 megawatt, are needed to pursue applications, including anti-cruise and ballistic missiles. This increased power reduces the time the laser needs to be held on target and allows for effective targeting at an increased range. As a result, designers are constantly pushed for higher power systems. Next slide, please. So what role do capacitors play in all of this? So when we think about how we can power a directed energy weapon on an aircraft, a truck, or a battleship, the thought of using a battery may come to mind. Battery technology has matured significantly in recent years as their energy densities have continued to improve. Now, batteries can hold a lot of energy, but they cannot release that energy quickly. Therefore, they have low power density. Similarly, typical generators on mobile platforms are not designed to handle the high levels of power required by high power directed energy systems. Now, capacitors don't store as much energy as a typical battery, but they do deliver their stored energy very rapidly, making them ideal for high power applications. Batteries are relatively limited in their charge-discharge cycle life, whereas some capacitors have extremely long cycle lives. There are many capacitor technologies to choose from, so it's important to choose the best capacitor for each unique application. So due to their unique properties, capacitors play a vital part in directed energy systems. Next slide, please. So what is ESR and why is it important? The equivalent series resistance, or ESR, of a capacitor is a major factor that will determine its suitability for use within a directed energy system. The ESR of the capacitor is the internal resistance that appears in series with the capacitance of the device. If the equivalent series resistance values, the equivalent series resistance values range from just a few milliohms to several ohms, and they result in power losses, reduced efficiency, and instability of power supplies and regulator circuits. Now, directed energy systems often work by means of a very high current pulse. If the ESR of a capacitor is high, a lot of energy will be lost, which is typically in the form of heat. This phenomenon increases exponentially as the current increases. Therefore, high current pulse applications are very sensitive to ESR. ESR can also contribute to the capacitor's ability to charge and discharge rapidly. Some directed energy systems have aggressive duty cycles, meaning they're charged and discharged several times per second. If the capacitor has high ESR, its charging and discharging abilities are diminished, thus limiting the capabilities of a directed energy weapons system. Next slide. So let's talk about how we manage heat. Now, even when a low ESR capacitor is chosen, the current levels of powerful directed energy systems can be so high that designers must still take self-heating of the capacitors into account. If a capacitor overheats beyond its rated temperature, its lifespan becomes significantly reduced and its performance will be affected. Concerns regarding heat may require designers to implement thermal management solutions within their systems, typically in the form of heat sink, fan, or cold plate. Capacitors can be added in parallel to reduce ESR as well. However, all of these mentioned solutions add both cost and size to the overall system. It is good practice to specify a capacitor with the lowest ESR possible to reduce these losses while minimizing any negative impacts to size, reliability, and cost. Next slide. So another source of loss can actually be found in the wiring or traces on a PCB. Just like capacitors, the wiring and traces inherently contain resistance. The longer the wire, or the longer the trace, the higher the resistance, thus the greater the loss. Again, since current levels seen in typical directed energy systems are so high, they are highly susceptible and sensitive to this loss. It's best practice to place the capacitor as close to the emitter as possible to keep wires and traces short to minimize losses. Physically large capacitors may pose a challenge when trying to keep this distance short. However, smaller, more power-dense capacitor options will aid in this design task. On top of that, if a low ESR capacitor is chosen, that solution turns into a win-win scenario. Next slide, please. So swap, otherwise known as space, weight, and power. The swap savings are commonly a critical component for directed energy systems. These systems are commonly deployed on naval, airborne, or land-based platforms. Now, one attribute that all these platforms share is that they are space limited. They are typically designed on existing platforms that are retrofitted to include the directed energy weapon systems. The addition of the weight and volume to an already space-constrained platform poses a design challenge within itself. So every opportunity to select components that reduce size should be considered. The P, or power, in swap should not be taken lightly. The previously mentioned existing platforms may have been designed decades ago, and their power systems really were not made to support these power-hungry directed energy weapons. Minimizing power losses using the methods described on previous slides is key in reducing the demands on the limited available power. Now, while a capacitor may work wonderfully in a lab environment, to prove a concept, it may be a poor choice for use in the field. There are many capacitor technologies that offer both power density and energy density, delivering a compact and lightweight solution. Next slide. So it's important to note that ESR and capacitance can change as a function of temperature. As an example, shown here are the temperature versus ESR and temperature versus capacitance curves, which can be found on our website at quanticevans.com. For part number TDD 4125602, which happens to be a 125 volt, 6 millifarad hermetically sealed capacitor. As noted by the capacitance versus temperature curve on the bottom left, at minus 55 degrees C, the capacitance value is actually approximately 35% lower than it is at room temperature. At 125 degrees C, our capacitance increases by about 48%. In the bottom right, ESR versus temperature curve, the ESR drops significantly during operation at high temperatures and increases at operation at low temperatures. Now, understanding these characteristics are critical during the design phase. It's important to ask the manufacturer for temperature versus ESR and capacitance curves to understand how the capacitor will behave in varying environments. At high altitude in space, designers usually need to consider how the capacitor will behave at low temperatures, meaning the circuit must be designed to operate with the ESR and capacitance values at their respective operating temperatures, not just at the room temperature rating. Next slide, please. So different capacitor technologies vary widely in their operating life. The capacitors used within directed energy systems commonly must survive thousands or more charge-discharge cycles. Designers must be aware of a capacitor's wear-out mechanism in common operating life. Now, some capacitors can actually fail open, and others may fail short. Even in some extreme cases, some capacitors can even catch fire during a failure event. Designers must understand what type of failure mode the capacitor might exhibit in order to mitigate risk during these catastrophic events in case of failure. Now, depending on the application, hermeticity may be required. For example, in high altitude applications, hermetic capacitors are often specified in order to survive these environments. Now, some aluminum electrolytic capacitors are not hermetically sealed, Therefore, their electrolyte can dry out over time. In such a case, preventative maintenance must be performed. However, that can be undesirable as performing this preventative maintenance can add cost and can impact system readiness and availability. Now, there are several aspects to a capacitor life that come into play. Some defense applications may sit dormant for years, and when they are used, are very short in operating life. Designers must consider the capacitor's shelf or storage life to ensure that the capacitor is ready for use when it's needed. Some capacitors are limited in storage life, whereas some have an unlimited storage life. Ensuring that the capacitor is rugged enough to withstand shock and vibration conditions commonly seen in the application is important. Now, even when the most rugged capacitors are chosen, they can become damaged if they're not properly secured to the circuit. Ensuring that the capacitor is mounted to the circuit in a way that protects it from damage during these shock and vibration events is critical. Next slide. So, as we've discussed, there's several different types of capacitor technologies to choose from. Each offers their own unique set of pros and cons. Each application has its own unique electrical requirements, operating temperature ranges, failure modes, and shock and vibration characteristics. So it's important to have a general understanding of how each type of capacitor operates in varying conditions. Now, here at Quantic, we have several capacitor technologies to consider when looking for a capacitor to optimize the performance of a directed energy system. Here at Quantic Evans, we manufacture hybrid wet tantalum capacitors. The hybrid technology actually gives our capacitors their designation as the most power dense in the world. Their rugged, hermetically sealed allows for operations in a wide variety of extreme environments. They are known for their low ESR, unlimited current handling capabilities, and these capacitors are well suited to meet the needs of the most demanding applications. Our hybrid wet tantalum capacitors are self-healing, and unlike some other capacitor technologies, they do not fail catastrophically. At Quantic Patron, we manufacture multi-layer film capacitors. These feature a construction very similar to that of MLCCs, or multi-layer ceramic capacitors, and offer electrical stability as well as mechanical robustness. They are lightweight, self-healing, so they don't fail short, and require little to no derating. They are also known for having the industry's highest ripple current density film capacitor. Now, speaking of MLCCs, at Quantic UTC, we have a wide variety of multi-layer ceramic capacitors. Our manufacturing facility is ISO 9001:2015 certified and MIL Standards 790 approved. Quantic UTC is equipped to perform testing in accordance with MIL PRF 39014, MIL PRF 20, and MIL PRF 55681 as required. Last but certainly not least, at Quantic ULEX, we manufacture a line of patented ceramic capacitors. This unique technology allows us to manufacture our capacitors with higher capacitance ratings using fewer dielectrics, improving temperature and frequency performance in a high reliability package. In fact, we can achieve 20 times the capacitance rating in industry standard sizes. Our capacitors are fully tested up to 50 gigahertz with a roadmap that extends to 100 gigahertz in the near future. Next slide.
Thank you, Misha. As we've seen today, capacitors play a key role in the performance of directed energy systems. There are many different variables to consider as different capacitor technologies are evaluated, including ESR, power density, and thermal mitigation. Misha and I have helped countless engineers choose capacitors for their unique applications and are glad to open the floor for questions. As I can see right here, there are 3 great questions that we'd be happy to answer. First question would be, what are typical methods to keep capacitors cool during high current pulsing applications? The most common method that we've seen to keep capacitors cool would be using a cold plate. Another option would be using forced air, such as a small fan, or by bonding a heat sink using a thermally conductive epoxy to the back of our capacitors.
Yeah, great point, Nick. I'd also like to add that our hybrid capacitors are very thermally conductive. In our testing, we've seen significant case temperature reduction by use of just a fan. However, in a very aggressive high current pulsing applications, the self-heating of the capacitor does warrant the additional cooling methods, as Nick already mentioned.
So another question would be, what is the maximum current rating of Quantic Evans hybrid wet channel capacitors? Our capacitors have no current limit, so the only limiting factor is temperature itself. We use 20 degrees C per watt of power as a general rule of thumb when we're doing our math. For full rated life, our capacitors can go up to around 85 degrees C case temp at full rated voltage. Or if you're using voltage derating, our caps can go up to 125 degrees C case temp.
Right, and as a matter of fact, our capacitors can be repeatedly crowbar discharged into a dead short without damage. And again, as Nick just mentioned, our capacitors are only limited by the temperature rise caused by our own internal ESR, which is already very low. So as long as you keep our caps cool, there is no current limit. If your duty cycle isn't even terribly aggressive, the capacitor self-heating becomes much less of a concern.
Absolutely. Next question would be, are supercaps the best choice for a high power pulsing application? While supercaps work well in this application, their limiting factor is voltage, which is commonly less than 5 volts. Because of this, to reach typical voltage limits, you'd have to put multiple supercaps in series, which not only raises your weight and overall footprint, but ESR. Our hybrid wet channel capacitors can achieve most cap and voltage ratings within one capacitor. Our cap range from 10 to 125 volts and up to 1 farad of capacitance in a singular capacitor. If your application requires either higher voltage or a higher capacitance, we can put any of our capacitors in series or parallel to achieve your needs. And I think that wraps up questions. So hit next slide. Thank you everybody for attending today. It looks like we're out of time. If we've missed any questions or if you'd like any further clarification, please feel free to contact either Misha or myself through our website by using Schedule an Expert button on our homepage, or feel free to contact us at info@quanticevans.com. Our capacitors are available for purchase on DigiKey or directly through us using the Request a Quote button on our website. Thank you.
Thank you, Nick. Thank you, Misha. This was a great session. Again, like Nick and Misha had said, if you have any questions, please feel free to contact us at quanticevans.com. Thank you so much. We hope to see you next time.